Welcome, ladies and gentlemen, to Multiple Integration, Example 2. My name is Mr. Joshua Davis, and I am the Math Healer. Thank you for joining me today. Let's move into the problem. Evaluate the double integral over the given region by using the method of iteration. Now we're given the double integral over a particular region of y times the square root of x dx dy, where R is the first quadrant region bounded by the given functions. We have y is equal to x squared, and y is equal to 2 minus x squared. Now, for your convenience, again, I'm going to ask you to pause the video and copy this problem. It'll make it a lot easier to follow along as we proceed to solve this and define the area that's bounded by these functions. So at this moment, I'm going to give you a few seconds to pause the video. Let's move on to the next page, shall we? Now, ladies and gentlemen, let's take a look at this graph of the area that's bounded by the two given functions that we have. Well, when we solve the two equations simultaneously to determine where the two curves intersect, we find that x is equal to 1. So these two curves intersect at the value where x is equal to 1. And when we take that value of x and substitute it into either equation, we find out that the y values are 1. So the point of intersection here is 1, 1. You will also notice that if you went over example 1, that this integral here, this region, fits a type 1 problem where the region is bounded by an upper function and it's bounded by a lower function, and the x values are bounded by a specific number. X in this case is greater than or equal to 0, less than or equal to 1. So this is a type 1 type of double integral problem. As we see here, the upper function is y equals 2 minus x squared. The lower function for this region is y is equal to x squared. That's going to become important. Now, since f of xy is continuous in R, we can interchange the order of integration. So here's what we know now. We have a particular region, and we want to take the double integral over that region for y times the square root of x dx dy. And now that we know that this fits a type 1 type of double integral problem, we're going to interchange the orders of integration. Instead of it being dx dy, it now becomes dy dx. And we now have the integral from 0 to 1 of the integral where it goes from x squared up to 2 minus x squared of y times the square root of x dy dx. Now, for the inner integral, we're going to integrate this with respect to y. So in this case, we're going to hold the square root of x fixed. We're going to treat that as a constant. And we're going to take the integral of y with respect to y. And again, keep the square root of x fixed and treat that as simply as a constant at this point. So going to the next line, since we are holding the square root of x fixed as a constant, we take the integral of y with respect to y. So the integral of y with respect to y is 1/2 y squared, and the bounds of integration goes from x squared up to 2 minus x squared. Now we're going to apply the fundamental theorem of calculus and substitute in our upper bound and our lower bound using the fundamental theorem of calculus. Now, after applying the fundamental theorem of calculus, we have the integral from 0 to 1, And remember, since we took the integral of the inner integral with respect to y, the square root of x was held fixed, and that was treated as a constant. Applying the fundamental theorem of calculus, we now have 1/2 times 2 minus x squared squared minus x squared dx. Well, expanding this inner function here and simplifying, we now have 1/2, we take that out because it's a constant, times the integral from 0 to 1 of x to the 1/2. Now we took the square root of x and we wrote it in its exponential form of x to the 1/2. Now within the brackets, after expanding this and simplifying, we now have 4 minus 4x squared plus x to the 4th minus x to the 4th. So we see here that x to the 4th minus x to the 4th, that's 0. So upon further simplification, we now have 1/2 times the integral from 0 to 1 of x to the 1/2 times 4 minus 4x squared dx. After multiplying through by x to the 1/2, we now have 1/2 times the integral from 0 to 1 of 4 times x to the 1/2 minus 4 times x to the 5/2 dx. We notice that the 4's are common factors for these two terms. So we factor out the 4. After factoring out the 4, we now have 4 divided by 2 times the integral from 0 to 1. Now we're left with x to the 1/2 minus x to the 5/2 dx. Simplifying and taking the integral of these two expressions, we now have 2 times 2/3 x to the 3/2 minus 2/7 times x to the 7/2. And we're going to integrate that from 0 to 1. So we did the integration. Now we're going to use the fundamental theorem of calculus and substitute in our upper bound and our lower bound by applying the fundamental theorem of calculus. So as a result of applying the fundamental theorem of calculus, we now have 2 times 2/3 minus 2/7. Now, simplifying that, we notice that the greatest common denominator is 21. And because 3 and 7 are prime to one another, I simply went 7 times 2 minus 3 times 2 for the numerator. So the numerator is now 14 minus 6. And for the denominator, we simply multiply 3 times 7. We get 21. So we now have 2 times 14 minus 6 over 21. We now have 2 times 8 over 21. And finally, our answer is 16 over 21. Ladies and gentlemen, thank you for joining me today. I hope that this example demonstration video instruction was clear and easy to follow and understand. And I hope I did a very good job of explaining it to you and bringing across to you the concepts that are being used. Please let me know if this was helpful. You can reach me at mathhealer@mathhealer.com. My name is Mr. Joshua Davis, and please have an excellent and outstanding and fun and great day. Thank you for joining me today.